Come on, psych. So we are back talking about special sequences and series, ways of representing sine, cosine, e to the x as a sum of infinitely many terms. All right, exactly, which is pretty cool stuff. So we just did a couple examples and talked about stuff. I want to actually pull up an Excel spreadsheet that I have. Since most of our problems will be related to finding the first, an estimate based off the first n terms, what I've got here is you plug in your value of x and it'll actually calculate the value of cosine or sine or e to the x based on it.
So e to the pi.
So e to the pi is apparently almost 11.13, right? Based off the first 5 terms. So the way I program this, the first term for e to that is always 1. This one is...
2 numbers there.
What did I miss?
3.141592356. Yeah,
I was just using Excel's version of pi. I don't know. But yeah, so I just programmed each of these values according to those formulas, right? And yeah, apparently fact is the function for factorial in Excel. And then what I do is I find the sum of those terms, right? So we just did pi over 3, so you could enter pi over 3 here, and then it does some thinking. Oh, maybe it, wow, I blinked. I done blunk, and it done thunkin' when I was blunking. And yeah, right there we got cosine is 0.5, lots of O's, 43. Sine, what is sine of pi over 3 equal to? Normally. Yeah. Square root of 3, well done, sir. Divided by 2. What did my formula contain? Oh, yikes, yeah. I need a parenthesis there, don't I? So, wow, that's pretty close. Pretty close there, if I might say so. So yeah, so this is a little thing. So if I wanted to figure out what is it when I take cosine of 5, I believe these are all in radians by default. Yeah, if pi was working, yeah, then that's radians, yep. So yeah, so I can send this to you guys as a Google Doc or something like that, and you'll be able to use that as well. So that way it can save you the calculations of plugging into the formula over and over. But I do still want you to kind of know these formulas and know how they work, stuff like that. So going back to this, check this out. Check this out. This is going to be so cool. Check it. Check. So let's discover, I guess, is what I'll call this. What is e to the I alpha? Where alpha is an angle. So, according to our expansion, for our e to the x formula, yeah, let's use Euler's formula there. So the first term is 1, right, from the exponential series, plus x, so that would be plus I alpha, right?
What if alpha was pi?
That's eventually where we might be going. And then we'll have, let's see, the next one's x squared over 2 factorial, so plus I alpha squared over 2 factorial. Right? And then plus I alpha cubed over 3 factorial. I want to at least get out to the 4th term here, or 4th. I alpha to the 4th over 4 factorial plus ... Okay? So you guys agree so far? I know. That's the only way I know how to draw them. It's my font style. So let's see. Equals. So 1 plus I alpha. Plus. What is I squared?
-1.
-1. Oh, okay. So this is minus I I guess I could call this I times alpha squared over 2 factorial.
No.
Oh, the I disappears. Right. Because it was -1. The next ones will have alpha.
Or you can use factorial.
Okay, what is I cubed equal to?
-I. So minus I alpha
Over 3 factorial. What is I to the 4th equal to? 1. So plus alpha to the 4th all over 4 factorial. Let's see. I don't have my next term written up top, but what is I to the 5th equal to?
I.
That's just regular old I, so this would be plus I times alpha to the 5th over 5 factorial. Now, what if I regrouped these terms a little bit, where I grouped the odds and the evens? So what if I grouped the even ones first? Well, even by exponent. So minus alpha squared over 2 factorial. And then let's see, next even term is plus alpha to the 4th over 4 factorial. And then the next one in this list would be minus alpha to the 6th over 6 factorial. And then it'd be plus ... right? So there's all of those. Now, all of my odd exponented terms are all of these have i's in front of them, right? All I. So are you guys cool if I factor an I out of that?
Yeah. And is there y?
Yeah.
That's sine x plus cosine.
I believe it will be, yeah. So this will be alpha minus alpha cubed over 3 factorial plus alpha to the 5th over 5 factorial and minus ... so on, right? So this is equal to, now this series we just saw a moment ago, notice the signs are even alternating, everything's identical. So is this one sine, you said? So that's just sine alpha, right?
I think so. Nor is that cosine.
Oh, that one is cosine. Yep, that's what we get for not just scrolling up and looking. Right, the even exponents was cosine. So cosine is even. So cosine alpha plus I times sine alpha, right? So if I plugged in alpha for all of those x's, that is in fact sine.
Isn't, what is that?
So that means e, we'll even write it down this way. E to the I alpha is equal to cosine alpha plus I sine alpha.
When were we doing that before? I feel like we used that like similar formulas.
You're correct, we did. We did see cos alpha plus I sine alphas before. I believe that was what, polar form was it back in the day? Yeah, polar form of an imaginary number. Complex number.
Terrible.
And actually, that's the first thing we'll do with this. That was this course, yeah. Man, yeah, a lot of stuff we're going to have to remember on this final exam now that we're thinking about it. So polar form. Let's write 1 plus the square root of 3i in expo form. So this is polar form. Well, actually, there's 3 forms. I guess this is complex standard form there. So let's figure out what we're doing. So for this is a bit of recall. We won't be doing many of these tonight. So a is 1, b is the square root of 3. So I need to find what r and theta was it? So r is equal to, do you guys remember how to find r? Square root of a squared plus b squared. I like how my r's look like square roots sometimes.
R is 2.
Let's see, there's an r. R is square root of 4, so that r is 2. And then what did we have? Didn't we have like tan of theta is equal to, was it y over x, b over a? This is saying it's the other way around, a over b. Yeah. Let's see, what would it be a over b though?
Ron has a video on this.
Because a is the real part, horizontal, b is the imaginary. Tangent would be, yeah, b over a. It's got to be b over a. Book might be wrong in this case. So tan alpha or tan theta is equal to b over a. So what is that for us? That means tan theta.
Well, that's y over x.
Right. Yeah. So square root of 3 over 1. So theta. What's theta equal to here?
Got a tan verse.
Tan verse both sides. When is tangent the square root of 3? Someone's excited about it. Let's see.
Degrees.
60 degrees, is it?
Yep.
Let's see. I'm going to hand trick this one. So let's see. Tan theta. Tan is the ratio of the square root of fingers to the left over the square root of fingers to the right. So when is the square root of fingers? Yeah, I think square root of 3 over the square root of 1 occurs at 60 degrees, my 60 degree finger there. So theta is equal to 60 degrees. So that means we can write this in the polar form as 1 plus the square root of 3i is the same as what? What it was r? Let's actually write that out. R times, it was cosine theta plus I sine theta. Okay? So there's polar form. Oh man, I'm running out of room. So our polar form would be 2 times cos 60 plus I sine 60. Right? However, if I want to write it in exponential form, so this is polar form, exponential form will be writing it in terms of e to something. So check this out. Actually, wait, what is e equal to? E to the I alpha is equal to this. Where do you see that? Right here. So it turns out exponential form is just going to equal r times e to the I theta. EIO.
Ryo.
Yep. So this in exponential form, if I can fit it, will just be 2 e I, and what's alpha in our case? 60. Craziness. All right, we won't be doing too many of those. Or, yeah, pi over 3 in our case, wasn't it? 60 degrees. I use 60 degrees. So, all right, this is where we're going to finally do the last derivation. So let's see. So what is e to the I alpha equal to? Again? Cos alpha I sine alpha. So let's discover an interesting property. Someone mentioned earlier. What happens if I plug in pi here? What is e I pi? Right? 3 of the most important numbers. E, I, and pi. Raising e to the I pi power. What's that going to be? Let's just plug in pi for alphas here. So that would be... Yeah. So let's see. Let's see how good we are with radians and our trig values. Cosine at pi. Pi is 180 degrees. Cosine is what?
0. Reference. No, 1.
Cosine is the same as the x-coordinate at 180 degrees. That is -1. -1, yep. plus I. Sine at 180 degrees, or at pi radians. Sine is the y-coordinate. The y-coordinate at that point on the unit circle would be 0. So we end up getting e to the I pi equals negative 1. Because I times 0 is 0. And this right here is pretty crazy. The way my professor liked to write this formula, he liked to write e to the I pi plus 1 equals 0. Or if you add 1 to both sides. And he argued that, like SETI, search for extraterrestrial intelligence and stuff like that, and all sorts of different satellites we send out in space, like we'll have like pictures of like man, what we look like, and all sorts of weird things. I don't know if you've ever seen those. Air and Space Museum sometimes has like stuff like that. But my professor argued that what we should be sending into space is this equation. To prove what our intelligence is. Unfortunately, these symbols would mean nothing to another species. Right? So it wouldn't actually really prove anything. So you'd have to overcome that issue there. But notice what I said earlier, it includes the 5 most important numbers.
It includes exponents, multiplication, and addition.
It includes the 5 operations, 5 most important.
I only see 3.
It's got addition, which is similar to subtraction. It's got exponents, and it's got multiplication. All right. Subtraction is the inverse of addition. Right. You can add negative numbers and accomplish that. Division is the inverse of multiplication. You can multiply by reciprocal to accomplish that. Right. So it's got, I guess you could call it 3 operations if you wanted to, and it's got the most important relationship, one relationship, which is equality. Right. So it's a beautifully elegant formula. I don't think any mathematician would have ever expected that to be true. It's crazy. And without having had these sequences and series to represent these values, like I wouldn't have even known what e to the pi I meant. Right? Like it's just like a really weird concept. But yeah, it is voted to be the most beautiful, elegant mathematical formula ever discovered by councils of mathematicians. So, 4 out of 5 dentists recommend it, I guess. What that means. So that's kind of interesting. One thing that we can end up doing with this, what if I take, let's discover again. So lots of like crazy concepts today, so I know that when it boils down, you're just kind of using those formulas for the most part for your homework. So e to the I pi is equal to negative 1. What if I ln both sides?
You what?
ln both sides.
ln both sides. Take the natural log of both sides. So I'll end up with ln of e to the I pi
Which is just I pi.
equals ln of negative 1. Using our power property of logarithms, I can take this exponent out front, and I have I pi times ln e equals ln of negative 1.
ln of e is 1.
ln of e is 1 because e to what power is e? The first power. So I end up with the statement ln of negative 1 is equal to I pi. And previously, we had said that you can't take the log of a negative. But it turns out that the log of negative 1 is equal to I pi, and using this, we can actually find logs of all negatives, or at least ln's. I mean, technically, I could have logged both sides. It'd be a lot uglier, but you could find a statement that is equivalent to that. So our last example, using this fact, good stuff here, evaluates the following. What is ln of, let's say, I don't know, negative 10 or something? And the way we can do this, I can break this into ln of negative 1 times 10.
Which is ln of negative 1 times ln of 10.
Not quite.
Or plus 10.
Right, the log of a product can be written as the sum of two logs. So that's the same as ln of negative 1 plus the ln of 10. Ln of negative 1, I pi, plus ln of 10, I can approximate on a calculator or whatever, or chart, 2.303. Bam. So now we can take logs of negative numbers. What? Come on, mind blown today at all? Anybody? This stuff is crazy. Craziness. Yeah. Definitely. I just want to scroll up and look at that equation again. How crazy is that? What? E to the I pi. Actually, I've heard a joke where someone's like, your mom was so dumb, she thought e to the I pi was 1. But it's negative 1. Come on. How good is that? It's pretty great. So anyways, thanks for watching, internet friends, and I think we're good. We're good. We're going to have to take a mental break.